Okay, so last time we talked about the specification of models with spatial dependence, particularly emphasizing the role of a spatially lagged variable in that specification, either spatially lagged dependent variable, spatially lagged explanatory variables, or spatially lagged error terms. And so by combining these, we ended up with different specifications. The two main ones, and the ones we'll see back several times, are a model with a spatially lagged dependent variable, which we call in shorthand a spatial lag model, and then a model with spatially dependent error terms, where we saw two major flavors. One is autoregressive and one is moving average, but basically any one of the spatial processes that we talked about last week are appropriate to be included as a model for the error terms. So today we shift gears a little bit and we focus on the other type of spatial effects, spatial heterogeneity. And basically what I'm going to do is just kind of a very high-level overview of what are different ways in which we can model and take into account spatial heterogeneity, starting with just very simple discrete ways of putting heterogeneity in the model, to more continuous ways where we have the variables changing as a function of other variables, or we put in random effects. So basically, the idea is to give you a general sense of what the landscape is in spatial heterogeneity. As I mentioned early on, one, I guess, good aspect of spatial heterogeneity is that most of these models can be tackled with standard econometric techniques. So there's no need for specialized estimation methods or anything like that. However, as I've also already mentioned a couple of times, one of the complications is that oftentimes it's very hard to tell spatial heterogeneity from spatial dependence. And we already saw a very specific example where if the weights are such that the number of neighbors is not constant, then then a spatial autoregressive process induces heteroscedasticity, induces heterogeneity, even though there isn't any there to begin with. So in terms of the readings, basically the last chapters in the book talk about spatial regimes, and there's a couple of special articles if you want to dig in a little further, something spelling out, a very old paper spelling out how spatial regimes are implemented and the concept of a spatial Chow test. You may be familiar with a Chow test for structural stability. This is a spatial flavor. And then a paper that, and I'll talk about that a little bit later on, addresses this notion of spatial fixed effects and the extent to which they actually take care of spatial autocorrelation, and the short story is they don't. And then kind of there are many articles on geographical weighted regression. I just wanted to mention that. I know a number of you, or some of you, have used this before, and I just want to put it into perspective a little bit. So let's first start by the basic concepts, homogeneity and heterogeneity. And in essence, this is a tension between a global perspective and a local perspective. So global perspective is a traditional notion of an equilibrium. There's a single equilibrium. The process is stationary, which means it has reached an equilibrium, which means that basically what you see is not going to change. So it's the same everywhere. Functional form is constant throughout. The coefficients are constant throughout. This is a kind of the ideal situation in that, to some extent, is this notion of general laws, right? You've reduced the complexity of reality down to E equal mc squared, and that explains everything, right? So that's the gold standard, is to have these general equilibrium theorems, or things that hold rules, laws, whatever you call them. At the opposite end of the spectrum is a local perspective that allows multiple equilibria, or maybe none at all, that stresses non-stationarity as opposed to stationarity, and that allows for variability in functional form or parameter values across the data set, right? And of course, we will be interested in the extent to which this has a spatial footprint, right? This is the same as what I said before when we talked about the covariance matrix. The covariance matrix has off-diagonal elements that are non-zero. Okay, fine. What does that make it a spatial covariance matrix? If there is somehow some structure, a distance decay function or a spatial process that yields a particular form for this variance covariance matrix. Okay. So the standard expression, just to give some notation, is homogeneity. That's the typical case. Everything is the same everywhere. Specifically, we, in a regression setup, even though we have observations for different locations I, the parameter vector beta is constant, and the error term is well behaved in the sense that it is uncorrelated, it's identically distributed, which is translated very specifically in that its variance is constant. So that's kind of the ideal world. Then on the other end of the spectrum is something which basically is unworkable, but people like to think about this sometimes conceptually. It's where everything is different everywhere, right? So you have the I subscript for each location. There is a different beta I for each location. And we could even have a different error term with a different variance at each location. We know that as heteroscedasticity, but also different functional forms in different subsets of the data, right? So that is, it's really more of a big data way of thinking. So the homogeneity, global equilibrium is, I mean, I don't want to be pejorative because it's actually a good thing. It's more of an old style way of thinking about the world where everything can be explained with one law or one rule. Whereas, you know, with big data, there's so much heterogeneity that that's not very realistic. So how do we deal with all this variability that may be in the data? Because saying that everything is different everywhere doesn't actually help us either, right? So what do we do about this? And the fundamental problem in statistical terms is referred to as the incidental parameter problem. And we've seen this already in the context of the spatial weights. Because, I mean, the bottom line is, if the number of parameters increases with the observation size, with the sample size. So if there is a different parameter for each observation, then as we have more observations, we have more parameters, and we basically cannot win that race. That's the bottom line. So this is often a misnomer when you deal with white variance covariance matrix. So the white or the sandwich estimator for standard errors deal with the problem of an individual different variance for each error term. You don't actually estimate that individual variance term, but you estimate a function of it. And so oftentimes the first time you see this, because it looks like you estimate individual variance terms, you think that you do, but in fact you don't because you can't. I mean, if you have a new value for each observation, then our usual trick, which is asymptotics, going to the limit and learning from larger and larger data sets, doesn't work because we always have more and more parameters. So solutions are really not solutions. They're, you know, as I like to say, they're cheating, right? So you cannot solve the problem as it is, replace it by a problem that you can solve, right? So we impose structure, and the structure basically boils down to discrete structure or continuous structure. So discrete structure is basically saying we take the data and we cut them up in finite subsets. For example, in our US counties data set that we use a lot, we could say south, non-south. So the south is different from the rest, and so we run basically two different models, right? Or if we have more information, we could have more subsets, right? If you study urban housing markets or real estate markets, typically these are not viewed as one market, but there are multiple sub-markets. So each sub-market has its own model and its own parameters, right? Of course, the tricky question is how many of these should we have, right? And how are they determined? How are they delineated? Are they delineated exogenously, like in the south, non-south? Pretty much everybody agrees where the line is. Or are they determined by the data, endogenously, which is where you have cluster ideas. How do you form clusters of the data endogenously? And there's a mixed modeling literature, but mixed modeling is a very confusing term and means different things to different people. But essentially, it's a situation where you can have, say 2 different models supported by the data, and you let the data determine for each observation which of the models it belongs to. This is a kind of thing used in marketing, for example, in market segmentation studies. And they're all discrete. They all, at the end of the day, say, okay, you're in A and you're in B, and you have 2 different models. Another way of conceptualizing this is more of a continuous variation, where, in a sense, you build a model for the model. So you build a model for the variability of the parameters, and that model is continuous in a number of different ways. You can model the variability of the parameters either by making them a function of something, or by estimating them locally on subsets of the data that change continuously, or you can replace them by a model with random variability. And so we have fixed effects and random effects. Fixed effects tie back into this discrete setup. Random effects tie back into more of the continuous setup, but not necessarily, right? And then the complication in practice, which I already mentioned, is that sometimes it's really hard to tell these apart, but in addition, one type is complicated by the other type. So you can have spatial heterogeneity with spillovers, with spatial dependence. Or you can have spatial dependence that has a different nature in different subsets of the data. One thing you do in exploratory data analysis is, for example, explore this by linking and brushing, and then you find sometimes that in part of the data there is very strong spatial autocorrelation, where in other parts of the data there isn't any. The classic Columbus data set that we use in class has that phenomenon for crime, for example, that in the city there's very high positive autocorrelation. As you move out, there isn't anything. So how do you model these kinds of things? So let's start with the discrete setup with spatial regimes. Basically, very simple, right? We take the data, we systematically define subsets in the data, and then we run a different model in each of the subsets. So, important to keep in mind, this corrects for heterogeneity, but it doesn't explain it, right? So, for example, you have in a lot of labor market studies, you have the Appalachian effect. In Appalachia, there is less labor force participation. Why is that? It's very complicated, right? But if you run a model with, say, an indicator variable for Appalachia, you got it fixed, right? You show everything else being the same, there is less labor force participation. Why? That's not addressed. So these models for regimes and for discrete spatial heterogeneity fix the problem in the sense that if you have different distributions, it doesn't mix them together. So that's the problem, say, if you have a bimodal distribution, right? If your bimodal distribution has 2 peaks. So if you take the overall average, you're somewhere in between the 2 peaks. So that average is not representative of either one of the 2 distributions. So here we say, okay, we cut it in 2. We have our 2 subsets. Each has its own mean. We're good. Why there are these 2 subsets, that we cannot address. And some of the other models try to at least get a better handle of that, of the why these different subsets exist. And so the regime specification goes from very simple things to very complex things. And the simple things are spatial fixed effects, of which spatial analysis of variance is a special case. So in essence, you have a different intercept in different subsets of the data. And there's, in an ANOVA set, you would have, say, 2 regions, and you're interested in comparing the mean between the 2 regions. You know, that's a simple t-test, but if you allow different variances, if you allow spatial correlation, then it's really kind of awkward to put it in a t-test or f-test kind of format. And so then you're much better off setting it up as a regression problem, which is exactly equivalent, but you can introduce spatial effects as we saw the other day. We can have spatial lag, we can have spatial error autocorrelation, and so on. And then full spatial regimes, basically everything can vary, not just the intercept, but also the slopes, the error variances, and so on. So I do want to spend a minute or two on this, because this is a very useful, quick and dirty assessment of difference in means. And one of the problems is that a traditional t-test is affected by the presence of spatial autocorrelation. So if, in other words, if you have spatial autocorrelation, the inference based on a classic t-test is not correct. Now, how incorrect, that depends, but there's a very easy fix, as I mentioned, is you set it up as a regression model with dummy variables for the indicator variables for the different regimes, and then you can run that regression model doing specification tests for spatial effects and incorporating them as necessary, right? And so then you have kind of the equivalent of a t-test, but with the spatial effects taken into account, so it's all done right. And there's basically 2 different ways of doing this, and I'm sure you know this, but just to make sure, is one is no constant term, but we have an indicator for each regime, so you're either in one or you're in the other one, and then you can test whether these 2 coefficients are equal. That's kind of a classic setup. The other one is more of a regression setup, is where you have one overall constant term, and then the regimes test is a test basically on whether the slope of the indicator variable, the coefficient of the indicator variable, is different from 0. In other words, is the regime different from the overall mean? That's a slightly different way of looking at it, but it's equivalent, right? It's the same. So in one, you're testing whether B1 and B2 are the same, which is more of the t-test logic. In this setup, which is more comfortable in the regression package, you test whether there is a difference from the overall mean. The overall mean is the intercept, right? So are you going up or down relative to the overall intercept? So you can set this up very easily and then run these kind of pseudo t-tests. Another context in which this comes up is when you have multi-level data in some sense. So not necessarily multi-level models, but data that group themselves nestedly in space. So a typical example would be, you know, housing units within census tracts. Or if you have individuals with, you know, diseases or some participation in a program grouped within neighborhoods, right? So then obviously there's an effect of the neighborhood on the individual behavior. Those were these contextual effects and correlated effects that we talked about the other day in the Mansky model, in the reflection model, right? So how do we bring these into the regression model? The easiest way is called the spatial fixed effect, where basically you tack on an indicator variable that is, you know, again, you have an overall mean and then a different one for each census tract. So all the households in the same census tract have a indicator variable, and that indicator variable captures all the effects of that census tract. So if you do that, you don't include census tract variables in the regression, right? That's superfluous. So it's one or the other, right? So if you have census tract variables like median income or, you know, density or distance to employment centers or anything like that, you might want to put that in the regression. But you have to keep in mind that there is heterogeneity on the left-hand side. So let's say you have 100 individuals living in a given census tract with a median income or a given distance to CBD, say, and you're looking at, say, the participation of these individuals in some training program. And so let's say 60% participate and 40% do not. But how are you going to explain that different participation with the same median income for the tract and the same distance to CBD for the tract? So that heterogeneity internal to the unit will spill over in the error terms and in potentially complicated variance structures for the error term, but it is not a standard situation. So one easy way to deal with this is just give each census tract a dummy variable and you're done with it. And this is called spatial fixed effects. And this is, you know, if you have a multi-level specification, that's kind of the, what is it called? It's not the, it's the non-pooling solution. So the pooling solution puts everything together, that's our homogeneity, and then the non-pooling solution would give every unit its own constant term, and then full multi-level modeling would treat that as a random effect and then model the variability across these units explicitly rather than just saying, here's a dummy variable, right? So, as I mentioned, as I alluded already to before, a common misconception in the literature, and you'd be surprised how often I have seen this, that an author or authors say, well, I have cross-sectional data, there's likely spatial autocorrelation. Of course, they don't test for it. But I put in spatial fixed effects, which corrects for spatial autocorrelation. Well, it does and it doesn't. And it doesn't more than when it does. It only does for very specific cases, and you can show this mathematically. It only does fix if you have autocorrelation of the equal correlation type, which is a kind of a side effect in panel data very often. In panel data, because of the shared time effects, you get a spatial correlation that everybody in the same time period is correlated with everybody else. That's a very particular covariance matrix with equal variances everywhere except on the diagonal, right? That's called equal correlation. Well, if you have a situation like that, then fixed effects take care of it, because fixed effects are just, you know, if you think panel data-wise, it's either fixed effects or random effects. So fixed effects, in fact, do take care of this internal correlation, but only then. So this is a pretty extreme case, which in my experience, if there is true interaction at the micro level, is not going to do it, right? If it's more like a macro level effect, you know, in the literature this is sometimes called common factors. So everything within a particular region affects everybody equally. In those instances, the fixed effects will do the trick. But if there is true interaction among the micro units within the region, then it will most likely not, because that true interaction will create a variance structure which is not constant, right? And so then you proxy that by a constant one, and, you know, strictly speaking, that's not going to be correct. The reason why this has so much traction in the literature is that in some cases where people actually do test for spatial autocorrelation, after introducing the spatial fixed effects, there is no more evidence of residual autocorrelation. So it has been fixed. This can be the case in specific situations, but is really an empirical matter rather than a general rule. And, you know, I have personally used this trick as well when it was just too complicated to deal with the spatial autocorrelation. And as it happened, introducing these fixed effects, you know, you run the specification test, there's no more evidence of autocorrelation, so you can move on and focus on the model itself, right? This tends not to work when the autocorrelation is of a substantive nature. As I mentioned the other day, if you have true interaction and the model is a spatial lag model, these dummies are not going to do it. If it's in the error term, which as we saw is not the same kind of problem, it's more of a precision problem, then you can get away. But still, you should base this decision not on some kind of general rule, but on specification tests in each particular example. So those are kind of the simple cases where the regimes are limited to the intercept, to the coefficient of the constant term, if you wish. So the full spatial regimes are a little bit more complicated, but still they're not very complicated. They basically boil down to you running a separate model in each of the subsets. So the classic setup, I use an example with two regions because if you do more, it just gets more complicated, but it's essentially the same idea. So we cut our data set in two. We have two subsets of the dependent variable. We have two subsets of the explanatory variables, each with their own sets of regression coefficients, and then we have two sets of error terms. So in essence, this just boils down to running two separate models. And if there is no connection between the two sets, in other words, if the, you know, none of the variables on the right-hand side pertain to the other region, as they might say in an SLX model, or none of the error terms are correlated across regimes, then there is absolutely nothing gained by expressing it like this rather than running two separate regressions. One for y1, one for y2. We're done, right? And then our interest is really on, is this really appropriate, right? So let's say we have two subsets of the data. Let's say we compare urban areas to rural areas, or we compare the center of the city to the suburban areas, right? We're interested in some phenomena. Could be education, going to private schools versus public schools, crime, you know, house prices, you name it, right? So since our gold standard is always to come up with these general rules, ideally we would like to find that even if we run these two separate models, there's no reason to, right? So our null hypothesis is that the coefficients are the same in both subsets. So that's a test on spatial homogeneity. It's just a test on homogeneity, but we call it spatial because our subsets are spatial. And then if we reject this null, we can reject this for any number of reasons, right? It could be different intercepts, which is the ANOVA setup that we had before, or different slopes, or both, right? What would different slopes mean? For example, in a hedonic modeling situation for house prices, hedonic model expresses the price of a good as a function of its characteristics. Let's say one characteristic is the square footage, right? So how much is a square foot worth in terms of the house if you have extra square footage? And let's say you find that in the center city that is very different from in the suburban areas. In suburban areas, space is cheap. In center cities, it's not. And so you would pick that up as a different slope, in this case, between the two subsets, right? So the classic test for this, you might know this from classic econometrics textbooks, is the Chow test. Is the concept here, and we'll see this again later when we talk about specification testing, is comparing two models. One is referred to as restricted, the other one is referred to as unrestricted. And this may seem confusing at first, but I have a very easy trick. Restricted means you restrict some coefficients to be 0. Unrestricted means they can be whatever they want. So restricted is always going to be the simpler model, the model with fewer coefficients, because you set some coefficients to 0. And unrestricted, you know, you let them be different. So in this case, restricted means that all the coefficients are the same everywhere. So you basically run one regression for the full data set. Unrestricted is you let them be different in each of the subsets. So you run 2 regressions in our example, and then the the test is basically derived from the sum of squares, the residual sum of squares in these 2 situations. So this is a classic Chow test as an F statistic. Now you can generalize this, and most econometrics textbooks have this, and I actually like this way because it generalizes very nicely to spatial models where, in essence, the only thing you have to worry about is that this V, which is the variance matrix, is the correct variance matrix, right? So we run the regression as 2 separate regressions. So we have a full vector. If you look at the beta vector here in the spelled out example, so you have the beta 1, 1, 1, 2, 1, 3, 3 coefficients from the first regression, and then 2, 1, 2, 2, 2, 3. And then you set up a system of constraints, of linear constraints on these coefficients. And if you read the matrix expression, you see this is the first row multiplies the first coefficient by 1, and then the matching coefficient from the second regression by -1. So this is nothing but is beta 1, 1 equal to beta 2, 1, right? And so you do all of these together, and then if you do a little bit of algebra, you can show that this is a chi-square statistic. It is a generalized Wald test in technical terms. And the key thing is to get this variance in the middle. So basically the variance is V, which is the common variance covariance matrix of all 6 of these coefficients. And then you pre and post multiply V by this matrix of 1s and 0s, which express the restrictions on the coefficient. So this is perfectly general. If you want to say, let's test if one coefficient is double another one, you just have a 2 in there instead of a 1, right? But we're interested in equality. And as I said, the nice thing of this approach is that it generalizes very easily to any model where you can come up with the V. Of course, that's the tricky part, right? So if we do this in a spatial lag model or in a spatial error model, the key will be to come up with the proper variance covariance matrix. But once we have that, the mechanics are exactly the same. It's just matrix algebra. So this is a general test on coefficient variability. So then, so far we've applied this to, you know, general linear regression specifications, but now what happens if we move to spatial models? It's a little bit more complicated because we know how to deal with the beta, so to speak. We know how to deal with the regression coefficients. But how do we deal with the spatial part of the phenomenon? Do we keep the spatial process the same throughout? So one spatial parameter for the whole thing, and the betas are different by regime? Or do we actually allow a different spatial process in each of the regimes, right? There's nothing favoring one over the other except simplicity, right? Although you do have to wonder, when you allow different spatial processes in each of these subsets, we may run into some conceptual problems thinking about asymptotics. Because all, as I mentioned sometimes before, and I will again, all the properties of the estimators and spatial models are based on asymptotics. And as we'll see next week when we talk about maximum likelihood, how do we go to the limit in space? I mean, it's not like in a time series you just go the infinite future. In space you go in two directions, in two dimensions, and so there's different ways of doing that. And then when you have regimes, you have to think to yourself, well, does this actually make sense that this process of going to the limit stops at the border between regimes? Just as a thought experiment, consider the counties in the US, right? And this is a little bit artificial because the counties are the counties, and as we'll see, that's not actually how you think about it. You think about it more abstractly, but let's think about the counties in the south and the counties in the rest. And so as we go to the limit is just by adding counties, right? But the regime thinking really implies that we cannot add counties from the south that spill over into the north. They have to go south only. They cannot spill over across the boundaries between the regimes. So, I mean, mathematically, and to write it down as a model is very easy to do. Conceptually, it may not make sense. So my personal preference is, unless you have really good reasons, theoretically, to separate the spatial processes between the regimes that you have, my preference is to have one process that deals with the spatial spillovers throughout, and then you deal with the heterogeneity of the coefficients separately, okay? But there are situations where, you know, you can argue that the interaction, say for legal reasons, cannot spill over into neighboring areas, right? Let's say if you have an actual border between two countries, and let's say you cannot trade between the two. Or, you know, the border is closed. You cannot go through, you know. You just can't travel across the border. So then you could say, okay, you know, there is really no point in thinking about spillovers across this hard border. But in a lot of our empirical applications, that's not really the case. You know, I have one example of a student that's talking to me. Her example deals with Israel and Palestine. And the whole thing is these are hard borders. These do not, right? So where does the spillover is limited, right? If you look at North and South Korea, for example, there is a hard border. There's no very limited spillover. So then you could have a regime regression, one for South, one for the North, and actually test the extent to which these relationships differ between the two countries with different spatial processes in each. So how do you write this down mathematically? It's actually very straightforward. It's a direct extension generalization of what we had before. The part to the right is exactly what we had before. Different x's, different betas, different error terms. And then we have a spatial lag plopped in front. And in this, the first case on the top, we have one row. The weights matrix pertains to everything, right? And in the case on the bottom, we split the weights matrices between the two subsets. There is no spillover between the two. So W1 stops at the border of regime 1. W2 also stops at the border. There's no spillover at the border. So this would be the case where you have counties and states, and for various legal reasons, there's no spillover between the counties in different states, right? That's a different model from having counties within states and allowing spillovers across the boundary of the states between the counties, right? Which is, you know, in the US, the borders between states are typically not very hard borders, so there's no good a priori reason to say that the interaction would stop at the state border. And then for the spatial error model is the same thing. You know, we have an autoregressive process that has one parameter for the whole data set, or it has two separate parameters. And this is, as I said, this is directly generalizable to any number of regimes. It just gets more complicated in the notation. So the thing, as I mentioned, to really think about conceptually is what are these weights? Are these weights what we call in PyCell and in GeoDa space regime weights? Regime weights are block weights. These are weights that stop at the boundary. So if you have, for example, all the counties in the US, each state would have its own weights matrix, and everything else is zero. There's no spillover between the weights, as opposed to one weights matrix for all the counties in the US, irrespective of the state that they're in. So that would be one spatial process. And then finally, as I already announced, the spatial Chow test is really nothing to it. This is exactly the same expression as I had before. The difference is getting the right V, getting the right variance. And that we'll talk about next week when we start with the estimation of these different models. Okay, now we move from the discrete domain to the continuous domain. And we'll start by looking at different ways in which we can let the coefficient vary. So this is getting a little closer towards explaining, although it's really explaining in quotes, because some of these models don't really explain that much. They just model the variability. So there's a number of different ways in which this can be done. I do want to focus on two. One, they're both at one point in time, the one still is, were very popular in geographical modeling. The second one, geographically weighted regression, because it is built into ArcGIS, is being used, and I hate to say sometimes abused, in a lot of contexts. And I do want to just kind of say what it's great for and what it's not so great for. And then the other one I just use as an illustration because the thinking and the setup, the formal setup, is very similar to multi-level models. And as I mentioned earlier on, since there are several multi-level courses around here, I don't want to spend any time on that because I could, but it would be somewhat duplicating. So this model goes back, as I said, quite a bit. And it's really interesting when you look at the thinking in econometrics and the literature in the 70s and the 80s. There was a lot of concern with this variability, and there are basically two different strands of dealing with it. One is the random coefficient strand, which ends up with complex variance component models, which then actually is the same generic structure you use in multi-level modeling. The other strand is to actually put variability into the coefficients themselves by making them functions of other variables. So this is just, in essence, a complicated way of creating interaction effects between variables. And the formal representation, if you've done multi-level modeling, you will recognize it as very similar. The main difference is that in the, or at least in the original form of the expansion method, everything pertains to the same spatial unit, whereas in a multi-level model, it does not. So in a multi-level model, you might have interaction of a parameter would be a function, in a county would be a function of state characteristics. In the Cassetti model, the parameters for a county would be a function of other county characteristics. So they create interaction effects. So the setup is actually very straightforward. You start with an initial model, which is the extreme heterogeneity form that I discussed before. So you notice there is a different beta I for each I. So classic incidental parameter problem, we can't deal with this unless we put some structure. So the structure is the second bullet, is the expansion equation, which basically specifies the variability of your coefficient beta across data points I as a function of other variables Z1, Z2, right? And that in econometrics is called varying coefficient models. And if you work it out, this very simple algebra, you end up with additional variables in your regression model that consist of interaction effects between the z and the x, right? So very straightforward, very easy to implement. In fact, if you didn't pay attention to the scale of these variables, this is exactly what you get in a multi-level model. You get these interaction effects, but then the variance structure of the error term is where all the complication comes in multi-level. In Cassetti's original work, there was no such variance component. I'll get to that in a second. So this is very easy to do. One problem, actually, if you want to get really high diagnostics for multicollinearity, try this. You know, you can get in the thousands the multicollinearity condition number. Because it is a problem. You're basically multiplying things, and if they don't vary enough, that's the problem you always have with interaction effects. If there's not sufficient individual variability, then your interaction effects will give you problems of multicollinearity. In the original, there's a whole literature. As I said, this was very popular at one point in time, and so there was a literature on refining this, and one way to deal with this is principal components. Principal components are very accepted in, say, sociology. They're not very accepted in economics. They're becoming accepted again in the big data world because they're a dimension reduction approach, right? The dimension reduction part, there's no controversy there. It works as advertised. These principal components are uncorrelated by construction. The problem is interpreting them. So principal component loads on different variables, so can be very confusing. And so there's all kinds of ways of dealing with this, you know, restricting the number of variables it can load on and stuff like that, but we won't go there. It's just for reference purposes. So if you then bring in the randomness effect, which is more of a what, say, econometrics would do, then you end up with the same kind of interaction effect and with the kind of variance component structure that looks very similar to what you have in multi-level models. So then the trick is how can you identify the separate variance components, and again, I won't go there. So that's one way to deal with the variability. It's you know, not very difficult to do. It's also maybe not that useful because if you put in too much additional variables, you have issues of interpretation with the multicollinearity. So the other approach, which can be seen as evolving from this, although it's a totally different way of thinking about it, is geographically weighted regression, or GWR as it's known. And this is really a special case of a local regression. It's a local regression, and I'm going to spend just a few minutes putting this into context because local regression is about attribute space. So it's about the space of the variables, the y's and the x's. Geographically weighted regression is about geographical space. So whereas classic local regression exploits local subsets in the attribute dimensions, geographically weighted regression exploits local subsets of the attributes but in geographic space. So it's kind of, you can think of it almost like a dual perspective, right? And so the way you do this is pretty standard. You use a kernel-based regression. A kernel is a weighted averaging, a weighted smoothing, where the distance determines the extent to which observations are down-weighted. That's a kernel function. And typically you do this up to a certain bandwidth, which is like a critical distance, how far you can go. Now, these concepts of a kernel and a bandwidth originally come from the attribute dimension. So the bandwidth would be how far from X you go, not how far you go in geographic distance, but you can easily transpose this concept to geographic distance, and that's what GWR is. Okay. So let's just backtrack and look at the essence of the idea of a local regression. Let's say you have you're interested in the conditional expectation. You know, that's what a regression is about. What is the mean on average of my dependent variable conditioned on knowing some additional variable x, right? And let's just specify it as very simple as, you know, we have a relationship m unspecified. This is not a linear regression, this is just unspecified, between x and y. And we want to know what is y on average given x. And the simplest case is when we have, let's say, only two values for x. And I pulled this example out of a regression, hedonic regression setup. Let's say we have only two values. You know, in a hedonic regression, we have a patio or we don't have a patio. So we have all the houses. We have all the houses with a patio and all the houses without a patio. So we're interested in the average price of a house given that it has a patio, or given that it doesn't have a patio, the conditional expectation. So that's very easy in a way, because we can think of this, and you know, usually when you see this kind of thing in a scatter plot, you say, oh no, I don't want this, right? But in this case, it's actually useful. So we have two values for x, and then we have a whole bunch of values for y, right? So what's the average of y when x is 0? We just compute it. It's very easy. And what's the average of y when x is 1? We just compute it. So anytime we have a setup where we have discrete categories in x and a continuum for y, you know, let's say you categorize people in markets, right? In marketing, you may be familiar with this prism notion, you know, blue collar, yuppies with children, retirees, you know, that kind of stuff. So these are all categories, and then you want to know how much on average they spend, say, on groceries, right? Or on particular kind of groceries. If you say you're a Whole Foods, you want to know how much people will spend on organic produce in each of these categories. So you know who they are, you know what they spend, you have your bars, you're done, right? So what happens if it's not that clear, if x is actually continuous, right? So then you have a situation where you're going to expand this notion and say, rather than taking the whole continuum, you're going to make a band. And if you've did my class in the fall, we did this way with geostatistics. We take a distance band and we take the average within that band of everything within the band, right? So here we're going to do the same thing. We take a little band of x's and we take the average of the y in that band. So that's this situation where you can think of this as kind of a moving band moving along the x-axis. This is bivariate, it's very simple, right? Along the x-axis, and then for each of these points in there, you take the average of the y, and that gives you the curve, the local regression curve. And so then you can extend that to, rather than taking a simple average, taking a weighted average, where you weight the observations that are closest to your target x, the center of the band, more than the ones that are further away. So that's where the notion of a kernel regression comes in, where you can think of this as a moving window along the x-axis, you know, focused on different values of x, and taking into account all the y's in the band, but counting the ones for the x's that are further away less than the ones that are closer by. And so for every one of these little windows, you have a different estimate of the average y's, weighted average y's, and that gives you your curve, local regression curve.
Do you need a specific sampling for doing that?
Yes.
Because
Right.
there are few observations.
You need two things, right? You need the band, that's the bandwidth, and you need the function by which you downweigh them. That's called the kernel function.
Yeah, but more the data that you're
The what?
Like the data we use are usually like survey data.
Yep.
And so I'm guessing that these bands have like few information inside, like we can only get like 20 observations per band or something like that.
Well, see, that's the critical thing. So it depends on how dense your points are relative to the x-axis, right? So the bandwidth determines how far you go, right? And there are two concepts in terms of bandwidth. One is one size fits all. So if you say, I'm going 10 in each direction, whether I have 500 observations or 20 observations, right? The other one is an adaptive bandwidth, where you go far enough to have sufficient observations to have a reasonable estimate. So in an adaptive bandwidth, in your situation, if you only have 20, you keep going until you have something that you're comfortable with. And then there's a whole literature on this. There's all kinds of rules of thumb on determining what is an optimal bandwidth, but the bottom line is, to do sensitivity analysis to really see how much it matters. And the general rule is that the function itself doesn't matter that much. The bandwidth does matter. So just to make it explicit, we're back into our average of the y's for a given x0, but we actually take xi's that are different from x0, but only a little bit, and then this k function downweighs them as we move further away. So it's a distance decay in attribute space, right? We're still in attribute space. So then these kernels will revisit this. They all have fun names. Epaneshnikov, bi-square, triangular is a very easy one, also called Bartlett weights. They just basically go down linearly with the distance. You have Gaussian ones. A Gaussian one, unlike, say, a triangular one, you give the bandwidth, and so it goes down up until you reach the bandwidth, and then zero beyond that. A Gaussian one is a bell shape, so that in principle keeps going, although obviously the weights you're giving to points that are far away become very small. And so the concept of a bandwidth doesn't really exist for a Gaussian kernel because it never goes to zero, right? A triangular goes to zero, that's the bandwidth. Bell shape never really goes to zero, so what is the bandwidth? And then for those kinds of functions, the standard error or the variance is used to define the bandwidth, because that, in essence, gives the spread around your central point and how quickly your weights decline, with distance from the central point. So that's a general concept. In a GWR setup, very cleverly, this is moved from attribute space to geographic space. So now, rather than working on this attribute dimension on the x-axis, we move in two-dimensional space. And it's a little bit different, and it's formally it's the same, but conceptually it's actually very different. And that is why the statistical interpretation is actually quite complex. Because in the attribute case, the example I just gave you, the statistical properties come from making that space denser, right? With your 20 points, you only have 20 points. Well, go out and do some more surveys. Maybe you get 50 or 60 points, right? That's the rationale. And as you get more of these points in closed space, your estimate gets better and better, right? That's how the asymptotic works. In space, the radius is geographically, but the x and the y's in that geographic space may not be representative or go to the limit in any kind of systematic fashion. And that's the complexity of the space stuff. So basically, formally, it's very simple. It's the same thing. So you have a kernel function that says I'm going to downweight the x variables that are further away from me locationally. So I take a point in space. I say, let's say 5 miles. I do a circle around it. I pick the x and y points in that radius and then run a little mini regression just for those points. Then I move to another observation, do my circle again, pick those x and y's, and run another mini regression. So for every location, that gives me, you know, here in this notation, ui, vi, that gives me a separate regression coefficient for each location, right, as a local fit. Okay? So then you can, of course, map this and do all kinds of stuff with it. But we get back to your problem, your question again, you know, how many of these points do we take? And in space, you know that points typically are not uniformly distributed. So if you have, you know, household surveys and you do them in a dense core of the city, you will have many more points than if you move to the suburbs and they're further apart. So if your distance is fixed, then you'll have many points in a given bandwidth in the city and very few points outlying. Now, where does this matter? Think for a second. You know, more points is more precision, right? So we are computing an estimate for each location, but the number of observations involved in those estimates is not constant. So each of these estimates has a different variance. That's not good, because that's comparing apples and oranges. So if you make a map of these coefficients, which is typically what you do, you really don't know what you have there. So the better practice, I should say, is to have a fixed bandwidth. No, sorry, the opposite, an adaptive bandwidth, right? So that you go for a target number of observations so that each point has the same number of observations to get its local estimate of the slope coefficient. But then you run into another problem, because the whole issue of local regression is that there is local variability, and so with the adaptive bandwidth, the concept of local changes, right? So you may have the same number of observations and deal with that problem, but the whole concept of local in the city may be 2 blocks, and out in the suburbs may be a mile, right? So you can't win this one. You know, this is something you run into whenever the distribution of your points or observations is irregular. You know, we talked about this a little bit when we did the spatial weights, when you have the distance band, fixed band versus k nearest neighbors. You know, it's the same thing. So then, to carry out GWR, as I said, it has become, I think it's an excellent exploratory tool, because it gives you a sense of what is going on in the data in terms of how strong this assumption of constant coefficients, or how unrealistic this assumption of constant coefficients might be. There are, however, some issues. One is the choice of the bandwidth. You know, that's the same thing you always run into. And that gets more complex when you move to a multivariate situation. Because, you know, most of the local regression stuff in the non-parametric literature was initially developed for simple bivariate setup. And, you know, that's also the one I used as an illustration. But if you have multiple variables, then each of these variables could conceptually have its own bandwidth. And that creates problems of, you know, what are the statistical properties of all these estimates? How do you get significance tests? And this is, I say there's still several theoretical loose ends. There are approaches out there using cross-validation and computation-intensive approaches like that, but the ultimate problem is, what is the precision? How does the precision vary throughout the landscape, if you wish, especially if you have multiple variables? Because in a multivariate setting, as you probably know, the precision of one estimate is not independent of the precision of other estimates. Everything hangs together, and so that is actually can be quite complex. But I think it's an excellent way to visualize potential parameter heterogeneity. I would be very careful in the interpretation. You know, as always, you know, if it's very clear, you're probably okay, but if it's on the bubble, there are issues with p-values, there are issues with non-constant variance. There's still some theoretical issues that need to be worked out. And GWR has been applied in a number of modeling setups, not just linear regression, but things like count regression, logit regression, and so on. So these issues just kind of get more complicated when you move to those kind of models. Okay, random effects, the last topic. So in that same literature in the 70s and the 80s, one way to deal with this unrealistic assumption of fixed coefficients is to let them be random. And the classic random coefficient model specifies, again, we have our beta i's, one for each observation, as a function of some mean effect, beta, an average effect, with a random term. And then the whole thing is, what is this random term? Is this random term heteroscedastic or homoscedastic? Is it correlated? Is it uncorrelated? And that's where it gets interesting. So the traditional random effects model, which is actually the model behind the Broich-Pagan test for heteroscedasticity, is a simple additive error term, which then yields this heteroscedastic error, which is a function of the square of the explanatory variable. So that's the Broich-Pagan test, in essence, is a significant test on the slope of xi squared. So if that slope is 0, then the variance is constant and you don't have a heteroscedasticity problem. So this is kind of the classic thing. How do we bring spatial effects in here? Before we get there, a generalization of this, and you may see this in the literature. In some literature, this is called mixed linear models. As I mentioned the other day, mixed models is messy. Means different things to different people, but in this particular context, we can have a fixed part, the x beta, and then a random part, where z is a design matrix. This design matrix could be, for example, in a multi-level context, corresponding to different nestings of the data. But the important thing is that the design matrix has something which is a coefficient, but it's not really a coefficient, it's a random term. And this random term typically has a mean of 0. You set it up to be that way. So you're not really interested in the average effect because the average effect is 0, but you are interested in the variability. And particularly, at least in one literature, you're interested in the components of the variance. So what are the different parts of this variance and how can you attribute it, say, to within group effects versus between group effects and all kinds of things like that. Now, as we saw the other day, this is all the error term, so it's all about precision. So in a big data world, this all goes away because you don't, unless you are interested in the variance components, they become so small that they're basically not very interesting anymore. So spatial random coefficients get very complicated very quickly, and the only way to really deal with this satisfactorily is in a Bayesian hierarchical setup. So you can make these random coefficients, function of a mean, but then build in autoregressive structures. I did this at one point and I gave up on it because it was too complicated. So the main way in which this is done is with additive or sometimes multiplicative random effects. So it's the same structure as before with the random coefficients, but now, we play with this random term, the phi and I. And here we can put all kinds of interesting spatial effects. And the classic Bayesian hierarchical model structure, it's called the BYM model, which stands for Bisag, York, and Mollier, which are the authors of a paper. Basically spell out this model that is not identifiable. If you listened to me before, you will remember that any time you see a sum or a product of two parameters, you're out of luck because we can flip these two around and you can't tell the difference. So you can model the sum as an entity, but you cannot model the two pieces separately. And this is often a big source of confusion when people enter the Bayesian literature, because in Bayesian models, the parameters don't necessarily have to be fully identifiable the way they are in traditional, say, econometric literature, where there's a major emphasis on identification and being able to tell one parameter from another. So typically, the spatial dependence is put in one of these error terms and the heterogeneity in another. But remember, in a linear model, these are not separately identified. In some nonlinear models, they actually are. So that's something to keep in mind. That's where their popularity comes from. And to close, I want to get back to this count regression model. Remember, or maybe you don't, but at the very end of the discussion of the conditional models, I mentioned a number of different auto models, auto-logistic, auto-Poisson. And I also mentioned that the auto-Poisson model only allows for negative spatial autocorrelation because of the restrictions built into this conditional setup with the Hammersley-Clifford theorem and all that stuff. That is modeling the counts explicitly. So you model the dependence in the counts. Here we don't. Here we move one level away from it, and we model the dependence through the intensity parameter of the Poisson process. And let me, in a so-called random effects specification, and let me illustrate this. And this, this is kind of a classic example. So the probability that a variable equals a given number of counts is the Poisson regression. So e to the minus mu, mu is the mean, mu to the power y, y is the counts, divided by y permutation, right? And the way this is typically done in econometrics and in statistics, rather than modeling the dependence of the y directly, you make u a function of some other terms. So one problem in count models is heterogeneity. So you see this, for example, if you do point process models. So the key parameter is the intensity of the point process. So you can think of intensity, how many points are in a given standard areal unit, right? And in a classic model, the intensity is constant, which makes for very weird point processes. Most real processes have some form of grouping where you have higher densities in some places and lower densities in other places, right? If you look at the locations of liquor stores, the locations of convenience stores, Twitter messages, these are by no means constant uniform intensity. So the interest then is in modeling the varying intensity and say, you find some variables, some x's, like median income or something, access to subway stations, things that make sense. And then you plug that in to a model for the intensity. And typically, this is how it's done because the log of the intensity then becomes a linear model. If you take the log, the exponential goes away, and that's typically the setup for a count model. That's how you set it up. And then you estimate the parameter beta, which then explains how the intensity varies across the data set, right? So there's no random effects in there. This is, this is a fitting exercise, right? You find the best fit value for the beta. Now, if you think of it as a random effects exercise, then we can do all kinds of fun stuff, right? So now it's not just x beta anymore, which is the mean, but now we say that this intensity also has additional unobserved heterogeneity, which we put in one of these random effects, and then it also has spatial autocorrelation, which we put in the other one. And typically, this is where we use these conditional autoregressive models, which in essence what they say is that the intensity of the process will be correlated spatially, but not directly, instead through some additional random effect, right? So this random effect will make on average, they're all the same, right? But if you do in a Bayesian thing, you do drawings, then you will be drawing these random effects, and you will be drawing them from a distribution that is spatially correlated, which means that the intensity will show a spatial structure, right? And we know from last week that the spatial structure in the conditional process is everything else being the same, less than the spatial structure in a simultaneous autoregressive process, right? And that will have implication for the interpretation of the coefficients. So that's it. That's how you can do all kinds of fancy, complicated models with spatial autocorrelation through the random effects in the parameters.